All right, let's move on and talk a little more about general relativity. We said that general relativity is going to allow for the possibility of curved space. So now what we have to ask ourselves is what shape is the universe? Is the universe positively curved? Is it negatively curved? Or is it Euclidean? Is it our old familiar geometric shape that we have, that we're much more familiar with? And the current evidence is that it's very close to zero curvature, which means Euclidean geometry is a pretty good representation of the properties of our universe. So that's kind of, I don't know, surprising or disappointing. There was this possibility of these really interesting geometries, but it turns out that the geometry that best represents the largest scale properties of the universe is just our old familiar Euclidean geometry. Now we still definitely see effects from space-time curvature. One of the most common effects that we have is GPS systems. So, you know, GPS systems are based on satellites that are in orbit around the Earth, and they're based on timing. So the idea is if you place 2 or 3 or 4 different satellites and you have a GPS device that's in communication with those satellites, that if those satellites are just sending out very regular timing information with some highly precise clocks, then by determining the delay from each of those satellites to your GPS device, you can determine your location. And GPS is accurate, well, you guys know it's accurate to within a meter or so. It's just amazing how accurately they can place you. But general relativity predicts that time is not progressing at the same rate on the surface of the Earth as it is out in orbit. The gravitational field of the surface of the Earth is larger. So there is kind of a reference time that we might imagine with the universe, and that's picking a reference frame that on average is kind of at rest with the local sets of galaxies, and that you're far enough away from things that you're not disrupted by gravitational fields. As you get closer to planets or stars, or certainly by a black hole, something like that, time runs at a slower and slower rate. And so what happens is clocks near the ground are running at a slower rate, clocks in orbit are running at a little bit faster rate, and unless we adjust for that, it turns out that our GPS systems would no longer be synchronized. So GPS systems have to be programmed with formulas from general relativity to account for the differences in the passage of time at those two elevations. So it's a real thing. We really do use the equations of general relativity. Now, this is just, you know, this is one of those things you see where it says, you know, space is curved around massive objects. I'm not sure how well that really gives a feel for what's going on here. And then with this formula too, this is what's called the Schwarzschild formula, Schwarzschild's radius, and what it does is it tells us if I have a certain amount of mass and I'm able to compact it within a certain distance, there's going to be enough gravitational attraction then that that object will collapse down to a black hole. And the distance, the event horizon distance, is given by 2gm over c squared. So, you know, that gravitational force constant that goes way back to classical physics, that still shows up in our formulas for general relativity. And that still becomes a measure of how large gravitational effects are in our universe. Now, Yeah, and this slide has gotten this right. What happens is, at this radius, the curvature now has gotten so strong that the curvature has disrupted the geometry of space so much that there now are just no trajectories leading outside of the event horizon in the forward time direction. So if you're moving forward in time, there's no way to leave a black hole. Now, another prediction from general relativity, which is very apparent in our observations of the universe, is the expansion of space. So we've already referred to, back earlier in one of the previous lectures in this chapter, mentioned that we've got this expansion effect taking place. So, and it's an expansion of space. It's not that there was an explosion of material out into space, but space itself is getting ever more spacious. There's just more and more space all the time, which kind of runs against the direction real estate prices are going. But anyway, there really is a lot more space all the time. Now, to measure the effect of light traveling through this expanding space, what the textbook is suggesting is that we go back to special relativity and use our formula from there to determine how much of a redshift this would produce. And you don't want to do that because the formulas from special relativity are not allowing for the expansion of space. So this turns out to be the wrong formula to be using. So in your homework problems, we're going to derive a different set of formulas that you guys can use for the homework problems. So here is kind of a diagram outlining what this expansion of space looks like. So let's say we go back billions of years. Here's a couple of galaxies. Let's say this is now. So here's galaxy A, here's galaxy B. Maybe we're in galaxy B and we're seeing light from galaxy A, and right now it's arriving. Well, we know that that light left billions of years ago. So what did the configuration of the galaxies look like then? And it turns out that we now have, I would say, overwhelming evidence for the expansion of space, and that if we went back billions and billions of years, what we would find is that galaxy A and B were closer to each other at that time. And you're thinking, well, what does that mean? Are galaxy A and B racing through space? And general relativity says, no, that's not what's going on. What's happening is space itself is getting bigger. So as space expands, the galaxies are, for the most part, not moving at very high speeds. We can actually treat the galaxies as being almost at rest at certain locations in space. You know, location A and location B happen to have some galaxies at those locations. And as space expands, galaxies A and B are farther away from each other. Not that they're racing through space, they're just along for the ride. Space itself is expanding. So let's go back and see what happens here. So maybe at this point the light left galaxy A. Well, when the light left galaxy A, galaxy B wasn't that far away. But what the light found was, as the light traveled through intergalactic space, distances were all increasing. So let's imagine we put a bunch of markers, a bunch of space buoys out there, right? And then the light travels past each one of those space buoys on its way to galaxy B. Well, the first one didn't have to travel so far, but by the time it got to the next section, that had expanded. That's a longer distance. And then when you get to the next section, it's expanded even more. So what looked like a relative short journey turned out to be longer than expected. Now, we want to derive some formulas that allow us to keep track of this expansion and make accurate predictions about the properties of the light when it arrives. In particular, what happens is light traveling through expanding space redshifts. Now, it's not the same thing as a velocity-dependent Doppler effect that we saw in chapter 36. So this is not special relativity, it's general relativity. Space is expanding, and we need a different formula to tell us how much of a redshift we'll get. Now, we refer to this effect as the cosmological redshift. And that's because this expansion of space, as best we can tell, is happening uniformly throughout the entire cosmos. So we're guessing that, we saw those early pictures where the galaxies were kind of evenly spread out. And so the idea here is, well, it's kind of the, it's the wherever you go it all looks the same model for the universe. And so whenever light's arriving from other regions, from other galaxies, that light has been redshifted, and depending on how long it's been traveling, it will be redshifted less or more. Now, you might say, well, are the galaxies expanding then? As space expands, are the galaxies themselves being drawn out? Now, within galaxies, gravity is holding those together. So gravity is holding together the galaxies so that the distances between the stars within the galaxies themselves are staying pretty steady. When we look at galaxies, we can see definite sizes for those galaxies. We don't see evidence that the galaxies themselves are getting larger. So there's no expansion in the solar system, there's no expansion on planet Earth. All of that stuff is being held together by gravity. It's only when we get to these largest distances between the galaxies, light traveling through those regions ends up being redshifted when it's intergalactic. Now we're going to derive this formula, but let's. Well, I'm just going to write down the results right now so we can start thinking about these different concepts. So for the cosmological redshift, I want to define that as big R, and I want to define that as the wavelength observed upon arrival divided through by the wavelength at departure. So what's the observed wavelength at galaxy B compared with the original wavelength of the light when it left galaxy A? And again, it's a prediction from general relativity. This is what happens to particles traveling through expanding space. Some of their kinetic energy is lost due to the expansion of space itself. The formula that we come up then for calculating a redshift is equal to e to the v over c, where v is the relative rate at which the galaxies are separating. So remember the v's that we're calculating here, they're not speeds of galaxies racing through space, it's the rate of separation, and that's what it says. So relative rate of separation between the two galaxies. Now, this comes from kind of a simplification. What we're going to assume is that the expansion of space has just been going on steadily for the past 13.77 billion years. That's our best estimate of how much time has passed since that very early plasma phase, since the Big Bang phase that the universe went through. But it turns out that more detailed measurements by astrophysicists let us know now that at first the expansion was faster and then it slowed down for a while, but now it's picking up speed. It's never turned around and reversed. But if we take a look at pairs of galaxies that are separated now, if we follow those back in time, there was a time when they were moving away from each other faster, and then things slowed down, but again, now it's picking up speed. What we're going to do is make a simplification for mathematical purposes that the galaxies have been separating at a steady speed the entire lifetime of the universe. Now, when we make that assumption, what we can do is we can kind of map that out on a plot here. Now, this isn't included in the textbook, but so the textbook just said, we'll just use the special relativity formula. Turns out the special relativity formula and what we're deriving right here, they agree for low speeds of separation, but for really distant objects, the special relativity formula just doesn't get it right at all. So we definitely want to get something that's going to work for just making measurements to more distant galaxies. So here's the setup. So what we've got is, here is time. This is the plasma phase, the Big Bang. We're going to set that equal to t equals 0. And what we're going to assume is that now this particular setup, I kind of got the A's and B's reversed here, I guess, from the previous slide. I don't think that's a big deal. What we've got is light leaving galaxy B, headed back towards galaxy A. Now we're going to think of this in the reference frame of galaxy A. So what galaxy A sees is this. Galaxy A sees galaxy B leaving, 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 leaving. At some point light leaves, and then galaxy A watches that light come back to it. Or at least that's the way we're thinking about this. And at some point the light arrives. On this graph then, galaxy A is right along, and that needs to get labeled too. So galaxy A, there's an A right there. This is galaxy A located at x equals 0. And then, since we're assuming a steady rate of separation, V is telling us the rate at which galaxy B separates. Now, what we're going to say is, at some point, I'm going to call it T naught. Now, T naught's not 0. Remember, T equals 0 is over here at the plasma phase. And the light leaves at some T naught, and then it arrives at, I'm going to call today, right now, TH. Now, the little subscript H here is for Hubble time, and a lot of these measurements of redshifts, the earliest confirmations of the redshift were done by Edwin Hubble, the telescope, the Hubble telescopes. So there's a lot of Hubble stuff going around. And so I'm going to say TH, that's how much time there is today. And that's measured currently, I looked online, the number I saw come up was, the best number right now is 13.77 billion years, plus or minus a tenth of a billion or something, based on a number of kind of inter-confirming sorts of measurements. Anyway, so the light leaves galaxy B, it makes its way back to galaxy A, and what we want to do is be able to relate T naught with TH, and relate x naught with xh. What were the distances? How far were the galaxies separated? When the light left? When it arrived? And how do we calculate redshifts? So let's go back and say the redshift of the light coming back to us is the wavelength observed when it arrives based on the wavelength when it left. So that's the same formula as the previous slide with the subscripts rewritten. Now, what relativity, general relativity, tells us is that for a steady expansion, that ratio of wavelengths is proportional to how much space has expanded. So I can use xh over x naught, these distances, or what I could also use for uniform expansion is th over t naught. So I can actually use the timing information, or I can say the timing information is related to the redshift itself. So let's put some numbers in and see what happens. Let's say that we have, well, our measured Hubble time is 13.77 billion years, gigayears. That's since the plasma phase up to now. And let's say that we look at the hydrogen spectrum. Now, we did a lab with different types of materials. We looked at the spectrum of hydrogen, and we saw those lines show up. What a redshift would be is maybe observing, excuse me, making those same measurements of the hydrogen line. Let's say that the 410 line shows up at 740. So we can see that it's a redshifted hydrogen spectrum, and that the line that we know should be at 410 is now at 740. Well, that's an example of what a redshift would look like. And so we can take the wavelength values and use those to come up with the redshift. Now, for the numbers that are given in this example, we have a redshift of 1.80. Now, just a quick aside here. The textbook is using a different, they're using a Z value to represent redshift, which is, we'll see it in a few formulas. Anyway, they're using a bit of a different approach. I feel like this is simpler. It's just the straight, ratio between those two wavelengths, 1.80. What that says is I can take this formula up here, and I can use my measurement of the Hubble time and determine that the time at which the light left was at 7.65 billion years. So from this redshift formula right here, from general relativity for a uniform constant expansion, I'm finding out how long ago that light left, at what time the light left that galaxy. Now, if I want to find out how much time the light was in flight, I actually use this number. So the amount of time that the light has been traveling then is 6.12 billion years, and we actually use that number to say how far away the galaxy is. So we use this number and say, hey, if the light's been traveling 6.12 billion years, then that galaxy is 6.12 billion light years away from us. Now, in reality, that's not currently how far the galaxy is, because the galaxy has continued to separate. So the actual location is quite a bit farther than that, probably. And that also isn't the distance of when the light left. So the distance the light travels is some intermediate value between x0 and xh. And we would like to be able to go in and calculate x0 and xh. And we would also like to know what's the velocity of separation. At what speed are these galaxies separating? So, we got some interesting timing information from this stuff on the left side, but now we want to go after v, and we want to go after x0 and xh. So let's see how we might do that. So here again, galaxy A, here is galaxy B leaving, and then light heads back towards galaxy A. Now what's happening is, if we follow the path of that light as a function of time, its velocity of the light, dx dt, is going to be equal to the speed at which this galaxy was leaving minus c. So this starts us in another reference frame, and then the minus c is its speed back towards galaxy A. Now, the v that we have here initially is the velocity of galaxy B relative to A. But what this v becomes, as the light makes its way back towards galaxy A, this v is the rate of separation of each of the individual points that the light passes through. So as the light's making its way back towards galaxy A, it's finding regions of space that are separating from galaxy A at lower and lower speeds. Now, on this graph, if I pick any particular point that the light passes through, the velocity of separation of each of those points is given by x over t. So I can take this v and replace it with x over t. And then in this line I have multiplied through to get rid of the denominator. That gives me tx equals x dt minus ct dt. And then finally, what I can see is this is starting to look like the differentiation rule for the quotient rule for differentiation. So I'm bringing this factor over, dividing both sides by t squared. And so let's see, the quotient rule is bottom derivative top, top derivative bottom, bottom squared. So what I've done is I've set up that whole left side so it's following the quotient rule for x and t. On the other side, what I have now is minus c dt over t. And so I'm going to integrate both sides, and I'm going to start off at t naught, integrated from t naught to t on this side. This is actually x naught over t naught to x over t. And so what's going to happen when I carry out that integration is that I'm going to get x over t at the upper limit, and I'm going to get x naught over t naught at the lower limit. On the right side, I'm going to end up with minus c ln t over t naught. Now, let's think about what arrival looks like. What I have right now is we solved for x as a function of t for the light, which is handy. It's saying what trajectory will the light follow as a function of time, how far away will the light be. And when we start off, the light's going to be at a distance of x naught, and then as time goes by, the light's going to be coming closer and closer to us. What we're interested in, though, is really the arrival time. So let's set t equal to th. That's when the light arrives. Now, when t is equal to th, x is equal to 0. It's arrived, it's here. And making those substitutions, it gives us a formula that looks like x naught over t naught is equal to c ln of th over t naught. Well, let's remind ourselves that x naught over t naught, that's the same thing as the speed of separation. So if I look on my graph, this is the time that the light left. This is the location where the galaxy was. And x naught divided by t naught gives me the slope of that line. And the slope of that line is the rate of separation. So let's pick up everything on this page. There's another follow-up here. There's our same diagram. And now what we can say is, we do have to go back just a second here. So what we're also going to say then is V is equal to C ln TH over T naught. Now, TH over T naught, that's the same thing as the redshift. So what we're going to do to that last equation on this page is this becomes the redshift, and the left side of the equation becomes V. Just want to make sure we're clear on what's getting substituted, and there it is. V is equal to C times the ln of r. So if I'm seeing a galaxy that is producing light from a galaxy that has a particular redshift to it, I can calculate the rate of separation, how much is space expanding between us and them, and that's going to be given by C ln of r, where, again, I've written down r is the ratio of the wavelengths, it's also the ratio of the distances, and the ratios of the time of departure and arrival. Now, this raises an interesting question too. What's the largest speed of separation that we would ever encounter? And a first thought might be, well, the fastest speed of separation would be c. There's no such thing as going faster than c, but that would be wrong. And that's because if we're in special relativity, now special relativity assumes that time is somehow interconnected with space, but special relativity still assumes no spatial expansion. There's a fixed Euclidean geometry for the 3 dimensions of space. And we're in general relativity now, and general relativity allows for the expansion of space. And if I have a uniform expansion taking place, if I get far enough away, I'm going to find 2 locations that are separating at a speed faster than c. So in general relativity, there's no local speeds where you measure something traveling faster than c, but you can have relative rates of separation faster than c. There's no limit to how large that would become. In fact, if space is infinite, then you would see infinite rates of separation. So this works for all values of r. We don't have to worry about v being less than c. That's not a restriction. Now I'm going to work from these same 2 wavelengths before, which gave us a redshift of 1.80. And now that I have my velocity formula, I can calculate what the rate of separation is. And the rate of separation that we're seeing is going to be, the redshift we're seeing tells us there's a rate of separation 0.589 times c. That's how currently, well, I guess not currently, we've assumed a constant, or we've assumed a steady rate of separation for all galaxies. So this particular galaxy, these particular 2 galaxies, are separating at a rate of 0.589 times c. Now, how far away was galaxy B? How much separation did we have when the light left? And how much separation do we have when the light arrives? And those can be calculated as v times t naught and v times th. So here's the whole story. At time, 7.65 billion years into the universe, since the t equals 0 designated time, at a distance of 4.50 billion light years, the light left. The galaxies have been separating at 0.589 c the whole time, and before the galaxies even existed, those regions of space where the galaxies formed were already separating at that rate. By the time the light arrived, the galaxies were separated at a distance of 8.11 billion light years. Now, if we do go back and look at how much distance did the light actually have to travel, it's an intermediate amount. So the light actually had to travel for this much time, and the distance the light traveled was 6.12 billion light years, and that's how we designate how far objects are from us, is by using the distance light traveled in getting here. Okay, questions on any of this? So there's a couple homework problems on expansion rates, and the book introduces a different approach. Let's take a look at that. So the book uses what's called the Hubble law, and this is probably a more standard sort of way to present this, and says that the velocities are proportional to how far away the galaxy, the rate of separation is proportional to how far the galaxy is away, and that's reasonable, that's accurate. The Hubble constant is 71 kilometers per second. Now they've introduced this megaparsec, which is a distance measurement, which I haven't seen anywhere else in here. Anyway, again, I'm not thinking of working in terms of this. If you guys want to use the approach in the textbook, that's fine. For homework and for problems, you can do that. I'm going to stick with the approach that we've done here in lecture. I think it's easier, and I think conceptually it's an easier way to think about what's going on. So here's the expansion represented, and this diagram is just trying to point out that whatever galaxy you're observing this from your galaxy, it looks like all the other galaxies are leaving, right? Like, you know, was it something we said, something we didn't say? But all the other galaxies are headed away from us. And if we went to any one of those other galaxies, it would look the very same. So that's the idea of a uniform, what's called isotropic expansion. Here's an example of them using the Hubble law to determine the age of the universe. Now this also is assuming a universe expansion, kind of like what we did, and they're saying it's coming at something close to 14, where we use 13.77, which 14's a perfectly reasonable approximate number to use. Now, one of the predictions from the Big Bang is that if you go far enough back from the expansion of space, one of the predictions from the observed redshift, so this all traces back to observing the redshift, is that if you go far enough back in time, there would have been, well, this is kind of dramatic, this is saying it's the birth of the universe. What we do have evidence for is that there was this high density plasma state that I keep referring to that existed about 14 billion years ago. Now, there's different ideas about what conditions the universe may have been in preceding that, just leading up to that, what would have been the conditions of the universe. Now, there are kind of these, this is an interesting diagram in our text. Don't worry about it too much. What it's really saying is that as time goes on, what general relativity predicts, and it predicts very clearly, there's a set of differential equations that drop out of these field equations and make very definite predictions about what's happening in terms of temperature and what's happening in terms of rates of expansion. And the predictions are that the temperatures would have been really high at these early times. As space expands, temperatures are dropping off, and at some point you start to see familiar things happen, like atoms form. Electrons and protons slow down, and atoms form. Now, there's a period right here, and again, there's this general expansion taking place. There's this period right here for about 1,000 seconds, or about 100, sorry, let me think. Yeah, it's just for a couple of hundred seconds. So for about 200 seconds, there was a temperature at which nuclear fusion could take place. And during these, a 3-minute period, 25% of the protons fused into helium. So that's a prediction from the expansion model of space. So one of the predictions that came out of this was there should be about 25% helium, 75% hydrogen should be kind of the background abundances of elements in the universe. And now that we've made careful observations, we do see that ratio pretty much everywhere. Another prediction is during this 3-minute, 200-second nucleosynthesis process, there would have been trace amounts of deuterium and trace amounts of lithium isotopes that are left. And we have reached the point where we can do those measurements and they match up with the predictions. So very solid predictions were made, and decades later, observations verified that is kind of the abundance of some of these light elements throughout the universe. All right, so there's this timeline that they do. I'm going to run through this pretty quickly. It says that about 10 seconds into the universe, electrons and anti-electrons were no longer able to be formed. Electrons were still present, but the anti-electrons were not being formed. 3 minutes nuclear fusion, 380,000 years, atoms begin to form. Now, that first picture that we showed way back at the beginning of those background radiation in the universe, that dates back to this 380,000 years into the history of the universe. So the cosmic background are the photons left over. After a couple 100 million years, stars and galaxies begin to form at about 1 billion years. And then the question becomes, well, what's going to happen in the universe? Is it going to expand forever? Is the expansion going to reverse? And general relativity predicts, depends on how dense the universe is, how much material is out there. There's a critical density of material. If the density is higher than this, the prediction is that the universe could collapse. If it's lower than this, then the universe would expand forever. Now, when we look at what makes up the universe, what we find is kind of the familiar stuff. The protons, the neutrons, the electrons, the stuff we've talked about, apparently only makes up about 5% of what's called critical density. So that material by itself is certainly not enough to give the universe Euclidean geometry. Now, what we do observe is that the universe does seem to have more or less this Euclidean geometry to it. What are the missing parts? And so, dark matter, there's something out there that helps promote galaxy formation. And if we look at rotation rates in galaxies, there's something out there that's holding the galaxies together as they undergo rotation. And if we calculate the amount of material, it makes up about 20% of what we would consider critical density in order to have the geometry that we observe. Now, people have been trying to discover this, find evidence for this for 80 years. Theorists have looked at what kind of particles this could be. We don't have any confirmations of anything. So again, there's kind of like 5% of this stuff that we feel like we understand pretty well. The stuff in the standard model of particle physics is what makes up this 5%. There's this 20% of additional stuff that has a gravitational effect, but so far we haven't been able to observe it in any other fashion. And then, about 20 years ago, researchers at UC Berkeley, Saul Perlmutter, his group, made a remarkable discovery that instead of the expansion slowing down, the expansion is speeding up. So even in the case that the expansion never stops, we would still expect the expansion to slow down based just on gravitational effects. So this increasing expansion set off a whole new effort to try and understand what could be causing this increasing rate of expansion. Now, in general relativity, there is an additional term within general relativity that you can add in, and it's been referred to as dark energy. So it's like a potential energy that general relativity allows for. Einstein didn't use it. He said you could have this dark energy effect taking place, but at some point he decided it wasn't necessary in order to complete general relativity, and he thought it just made it more complicated. But now researchers have put that back into general relativity, and from that formula you can calculate how much energy there is, how much potential energy there is that's driving this ever-increasing expansion. And that comes out to be about 75% of critical. So on the one hand, if we add up calculations about how much dark energy there is driving the expansion of space, and we add with that the amount of dark matter that we observe based on galaxy formation and galaxy rotation rates, and you add that to the normal matter, we have just the right density. We have, within observation, we have the critical amount of density we would need to have Euclidean geometry, which is what we observe. So on the one hand, researchers said, oh, we got it all figured out, we know what the universe is made out of. On the other hand, we don't know any detail as to what this dark energy is. Maybe it's, maybe we just give it a name and say that's it. It's just this effect, or what the dark matter is due to. So kind of interesting that's where we find ourselves. Okay, and then finally, we don't know why any of the fundamental constants have the values that they do. So this is pointing out that things like the speed of light, proton, neutron masses, gravitational constant, if we fiddle around with these numbers, the universe would be very different. In some cases, nuclei might not form, atoms might not be stable. So it's kind of interesting. Right now we don't know. We've got a list of like 20, 25 fundamental constants, and we don't know why any of them have the values that they do. Kind of an interesting item to end on. So here's a summary of the chapters. I don't know that I'm necessarily going to read through all of this. Now there's one last homework problem. We have a few minutes left here, I realized. There's one last homework problem. It's the last homework problem of the course. It's the last homework problem of 3 semesters, 44 chapters of going through G and Coley. We only have a couple minutes, so I have to outline this quickly. And let me say, don't worry about this. This is not going to be on the midterm, and it's not going to be on the final either. It's just for fun. But we talked about neutron stars, and the effects on a neutron star. There's a gravitational force collapsing them, but there is this pushback that's happening due to the presence of neutrons. Now, what would stabilize, I guess the neutron stars here. So these forces are acting in the neutron star. Once the star has collapsed to a neutron star, the neutrons have kinetic energies, and what we can do is say the total energy calculation of a neutron star, or kind of the dominant effects of the energy, comes from the total kinetic energy of all the neutrons and the gravitational potential energy. Now, if the star gets smaller, gravitational potential energy goes down. And so gravity is trying to continue the collapse of this neutron star. But what's preventing that, what's putting on the brakes, is all of the kinetic energy of the neutron. So in this problem, this is a formula for the kinetic energy of a particle in a three-dimensional infinite potential well. So this is our infinite potential well that we're bringing back to use for this very last homework problem that you don't have to do, by the way. And so what we're doing is taking the kinetic energy of each of those quantum states and adding all of the neutrons together. So big N here in this integration, big N is the number of neutrons in our neutron star. And we can calculate the number of neutrons by taking the mass of the star and dividing through by the mass of an individual neutron. If we step through this, what we end up with is a net kinetic energy that goes up as the radius goes down. And it goes up by 1 over r squared. So as the neutron star becomes more and more compact, the kinetic energies have to go up. And that's what's putting on the brakes in the expansion. Now, on the other hand, gravity is trying to collapse this. So I did a layer by layer calculation of gravitational potential energy, carried that through. If you've got questions on this, we can talk during office hours, which I will get all of those posted and scheduled and posted. Carried that out and found out this is kind of the driving force tending to collapse the star if we now take those two opposing effects, combine them into our energy formula, and take a derivative, set it equal to 0. What it says is this: there's this gravitational collapse that collapses the neutron star to a point, but then the kinetic energy effect puts on the brakes and the neutron star stabilizes at some radius. Now, if you carry out all the calculations, don't lose any factors here, that radius value depends on the gravitational force constant, of course, the mass of the neutron star, the mass of the neutron, and Planck's constant. So Planck's constant, always keeping track of those quantum effects, and the formula we come up with, plugging those numbers in for, they told us to use a mass that's in the homework problem, 1.5 times the mass of the sun. That's how we write that. So 3 times 10 to the 30th, and the equilibrium radius for this neutron star worked out to be 10,800 meters, or about 11 kilometers. That's what they were suggesting we should get. So there it is, calculating the stability radius for a neutron star based on kinetic energy of neutrons, a very quantum effect, opposing gravity. Now, a couple things we could point to here: constants. Oh, look, what happens if the mass of the neutron star is higher? Well, if the mass of the neutron star is higher, the radius actually goes down. So you can see kind of where this is headed, right? It's the lowest mass neutron stars that are the largest, and if you keep adding more mass to a neutron star, gravity keeps collapsing it. And at some point, the neutron pushback, the neutron degeneracy, can no longer prevent the collapse, and you get a black hole. Everything collapses down. All right, again, last homework problem, good problem to end on. Kind of wrapping up the semester here, so again, make sure you're staying caught up with everything, and we'll end it there.